For years, scientists hoped that the oceans beneath the icy surfaces of Europa and Ganymede might harbor life. But they assumed any organic molecules would have to be produced slowly over billions of years by chemical reactions deep below the ice. New research reveals something more astonishing. The building blocks of life were baked into these moons from the very beginning. They didn't evolve life's ingredients. They were born with them. For decades, the search for life beyond Earth has focused on finding the right conditions: liquid water, an energy source, the right temperature. Scientists assumed that even if a moon like Europa had an underground ocean, it would need billions of years of chemistry to produce the building blocks of life. But new research has overturned that assumption entirely. Analysis of data from the Galileo and Juno missions reveals that Jupiter's icy moons may have been seeded with complex organic molecules from the very beginning, from the same disk of gas and dust that formed Jupiter itself. The ingredients for life didn't have to evolve. They were there from day one. Jupiter has 95 known moons, but 4 stand out: Io, Europa, Ganymede, and Callisto, the Galilean moons, first observed by Galileo in 1610. Of these, Europa and Ganymede are of particular interest to astrobiologists. Europa is encased in a shell of ice roughly 15 to 25 kilometers thick, beneath which lies a global ocean of liquid water containing roughly twice the volume of all Earth's oceans combined. Ganymede, the largest moon in the solar system, also harbors a subsurface ocean. Both moons experience tidal heating from Jupiter's immense gravity, which keeps their oceans liquid despite surface temperatures of minus 160 degrees Celsius. As we understand it, life requires 3 things: liquid water, an energy source, and the right chemistry. Specifically, complex organic molecules like amino acids, nucleotides, and lipids that can form the building blocks of cells. Europa and Ganymede clearly have the first 2: liquid water and tidal energy. The question has always been the third: where would organic molecules come from in a system so far from the sun, in oceans sealed under kilometers of ice? The traditional answer was that they would have to form slowly through chemical reactions at hydrothermal vents on the ocean floor, processes that on Earth took hundreds of millions of years. But the new research suggests they didn't need to form at all. They were already there. The study analyzed the composition of Jupiter's circumplanetary disk, the disk of gas and dust from which Jupiter's moons formed roughly 4.5 billion years ago. Spectroscopic data from Juno and modeling based on what we know about planet formation show that this disk was rich in complex organic compounds, including formaldehyde, hydrogen cyanide, and amino acid precursors. These are the same molecules found in interstellar clouds and on primitive asteroids. When Europa and Ganymede coalesced from this disk, they incorporated these organics into their bulk composition. The oceans that later formed beneath their ice shells would have been infused with organic chemistry from the very start. No billions of years of evolution needed. The ingredients were baked in. If Europa's ocean has contained organic molecules for 4.5 billion years, roughly the same amount of time life has existed on Earth, the probability of life having arisen there increases dramatically. Earth's oldest known microbial fossils are about 3.5 billion years old, meaning life appeared on Earth within the first billion years of the planet's existence. Europa has had just as long, with liquid water, energy, and now confirmed organic chemistry. The environment at Europa's ocean floor may be similar to Earth's deep-sea hydrothermal vents, where some of the most primitive life on our planet thrives today. These organisms live in total darkness, powered entirely by chemical energy, exactly the conditions Europa offers. NASA's Europa Clipper spacecraft, launched in October 2024, is on its way to Jupiter and will arrive in 2030. It will not land on Europa. Instead, it will perform nearly 50 close flybys, passing within 25 kilometers of the surface. Its instruments will measure the thickness of the ice shell, map the ocean floor using radar, and, critically, sample the plumes of water vapor that Europa appears to vent into space through cracks in the ice. If those plumes contain organic molecules, amino acids, or even microbial biosignatures, Europa Clipper could provide the first direct evidence that the building blocks of life exist in an alien ocean. It may be the most important space mission of the decade. The implications extend far beyond Jupiter. If moons can be born with the chemistry needed for life, then the same process likely occurred around Saturn, where Enceladus is already venting organic-rich water into space, and potentially around ice giants like Uranus and Neptune. It may have happened in other star systems entirely. The Milky Way contains billions of gas giants, many of which likely have icy moons with subsurface oceans. If organic chemistry is a standard feature of moon formation, then the number of potentially habitable worlds in the galaxy is not in the dozens. It is in the billions. Life may not be rare at all. We may just not be looking in the right places.